Thank you very much. Thank you very much for the introduction. Thank you very much for the invitation. It's always a pleasure to be here. So indeed, today I'd like to speak about real sextics, so real sextic curves in the projective plane without real singular points. But let's start from a general discussion of topology of real algebraic curves in the real projective plane. So this will be the first part. Real algebraic curves in the real projective plane. Should I write bigger or it's okay for everybody? Okay, so we take a polynomial so with real coefficients in 3 variables. We assume that this polynomial is homogeneous of degree d. And so this polynomial has the zero locus in the complex, in the real projective plane, and also the zero locus in the complex projective plane. So this is just the set of zeros of my polynomial in AP2. This is the set of zeros of my polynomial in CP2. So we have such a commutative diagram. And we'll be interested in several topological questions concerning this objects. So, let me assume, in fact, as I said, I'd like to speak about like singular curves. But let's assume that for the moment that the curve given by my polynomial is non-singular. By the way, so when I speak about a curve in the projective plane, so I mean such a polynomial considered all up to multiplication by a non-zero real constant, because we have the reals. And I'd like for the moment to consider non-singular curves. Meaning that f does not have critical points in, so I don't want to have critical points even, don't want to have singular points even for the complex point set. So let's assume that f does not have critical points in C cube without the origin. And so under this assumption, Rf, the zero locus of my polynomial, the set of real points of my curve, is either empty or one-dimensional. Sorry? No, it's the same. It's my polynomial is homogeneous. So under this assumption, Rf is either empty or one-dimensional smooth submanifold of AP2. So it's a collection of circles, right? Smoothly embedded in AP2. So if we're interested, so questions? So if we're interested in topological classification, so classification up to homeomorphism, and I mean I consider Rf, and I'd like to, provided that the degree is fixed, to classify possible topological types of RF. To describe topological type of RF, it's enough to tell what is the number of circles, right? So it's what is the number of connected components. There's another option is to classify our curves of given degree up to isotopy in AP2. And this, in fact, means that I'm interested in possible topological types of pairs AP2 RF. So now I'm asking how these circles can be embedded in AP2. And the last question I'd like to discuss today is classification of these non-singular curves of degree d up to deformation. So let's start with the first question. So the answer, okay, let's see how it works. The answer to the first question is given by the Harnack theorem. The Harnack inequality says that the number of connected components, so the number of circles of F is bounded from above by d minus 1 times d minus 2 over 2 plus 1. So this quantity is the genus of CF. So the genus plus 1 is this Harnack upper bound for the number of connected components of F. And in fact, Harnack proved more. So you have this upper bound, but of course you have also a lower bound. And in fact, you can do better. So if the degree is odd, then necessarily you have some real points. So the number of connected components is at least 1. And it's not difficult to show that once you know that this upper bound is sharp, and of course the lower bound is also sharp, to show the sharpness of this lower bound, you can take this Fermat polynomial. Once you know that the upper bound is sharp and the lower bound is sharp, you know, in fact, that all intermediate values, all integer intermediate values are also realizable. And Harnack, in 1876, he proved this inequality, and he proved also that this upper bound is sharp. So, in fact, Harnack completely answered to the first question, what can be the topological type of RF, provided that our curve is non-singular of degree d. So it's, as I said, it's a collection of circles, and the number of circles is an integer between this lower bound and upper bound. And the curves such that the number of connected components, or non-singular curves, such that the number of connected components is maximal possible according to this Harnack inequality, are called maximal. So if we have equality, we say that our curve is maximal. So now let's go to the case of degree 6, because it's the main subject of my talk. And let me discuss the second question, the question about the topology of AP2RF. In the case of non-singular curves of degree 6. And let's look at maximal curves. So what kind of picture in AP2 can we get if we consider a maximal curve of degree 6 in AP2? Okay, let's just check that everybody is still with me. If D is 6, what is this upper bound? 11. So maximal curves of degree 6 in AP2 have 11 connected components. And these 11 circles can be, so this collection of 11 circles can be embedded in AP2 in the following ways. So the first option is like this. So by the way, so if the degree of our curve is even, then each connected component of the real point set of our curve is embedded in AP2 in such a way that this connected component divides AP2 in two parts, a disk and a Möbius band. So the first option is like this. It's possible to have such a connected component and connected component embedded in AP2 in this way. So the connected component of our curve dividing AP2 into parts is called an oval. And so we have an oval, one oval inside, and when I say inside, I mean it is connected component of the complement which has a disk. And the Möbius band is outside. And 9 ovals outside. So such a curve was constructed by Harnack. In fact, when Harnack proved that his upper bound is sharp in any degree, in degree 6, he constructed a curve with such topology. There is another option. You can have 9 ovals inside and 1 oval outside. Such a curve was constructed by Hilbert. And there is the third option. It's possible to have 5 ovals inside and 5 ovals outside. Such a curve was constructed by Gudkov. It's a fact. It was Gudkov who completed the classification of non-singular curves of degree 6 in AP2 up to isotopy. So in particular, he constructed such a curve. And these are not just examples of maximal curves. So in any case, of course, these are not examples of curves of degree 6. I am just describing the topological type of such a pair AP2RF. So that's kind of schematic pictures. But these are not just examples. This is a complete list of possible topological types of pairs AP2RF for maximal curves, non-singular maximal curves of degree 6. And so you see that something non-trivial happens here. So in particular, I'm saying that it's not possible to take one of these ovals inside the big oval and put it outside. It will not work for maximal curve. And what is hidden in particular in this statement is so-called Gudkov-Rochlin congruence. So for any maximal non-singular maximal curve of even degree, so degree G, to underline that D is even as to K in AP2. one has the following congruence. So I will first write the congruence and then I will explain what I'm writing. So it's congruent. So this is the early characteristic of some part of AP2. And the congruence, this early characteristic is congruent to k squared. K is the half of the degree, modulo 8. So now I should explain you what do I mean by AP2. So my curve is given by a polynomial f. And for each point of the projective plane, I can try to evaluate my polynomial at this point. So it's not really an evaluation because, so if I take homogeneous coordinates of my point and I plug these homogeneous coordinates in my polynomial, I will get some real number, but this number depends on the choice of homogeneous coordinates. But what does not depend is whether I obtain 0 or not. That's why my polynomial has 0 locus in AP2. And for points outside of the 0 locus, what is also defined is the sign, because the degree is even. So if I multiply all homogeneous coordinates by the same non-zero real constant, I don't change the sign of the result of my evaluation. So I have what I will denote by AP2 plus is the set of points in AP2 where my polynomial is non-negative. And in the same way, I can define AP2 minus the set of points of AP2 where my polynomial is non-positive. No questions? Thank you very much. So, of course, this, for the moment, these notions are attached to polynomial, this polynomial f. And since I was speaking about a curve, this polynomial is defined up to multiplication by a non-zero constant. But it turns out that I can, well, so for the moment, I have just two subsets of AP2. So my curve divides AP2 in two halves. And I don't know which half is AP2 plus and which half is AP2 minus. But it turns out that exactly one of these halves is orientable. So there is one connected component of the complement of the real point set of my curve in AP2. There's only one connected component which is non-orientable. And so I will always assume that the sign of my polynomial f is chosen in such a way that AP2 minus is non-orientable and AP2 plus is orientable. So I assume that AP2 plus is orientable. So in particular, for example, on this picture, AP2 plus is like this. Okay, so now let's check the congruence just to make sure that I didn't make a mistake. So AP2 plus in this example is this annulus with 9 disks. The early characteristic is 9, k is 3, so we even have an equality. And so now you can do this easy exercise. You can use the Bezout theorem and the congruence to show that there are no other possibilities for the topology of AP2RF in the case of non-singular maximal curves of degree 6. So the Bethe theorem and the congruence are enough to exclude all other cases. Of course, then you should, if you want to complete the classification, you should construct curves realizing this topology. But for the restriction part, the Bethe theorem and the Gutkov-Rogin congruence is enough. Questions? Okay, so now let's speak about deformation classification. By the way, I should say that, so I said that Gutkov completed the classification of curves of degree 6 up to isotopy. And then Viro obtained an isotopic classification of non-singular curves of degree 7 in AP2, and 7 is the, up to now, is the maximal degree for which we know such a classification. So, isotopic classification? Sorry? It's still not finished. There are still, it's, so as far as I understood, there are 4, but surprisingly, the number of cases changes from time to time, but I think that the value is 4.
But not the number of publications.
Sorry?
Not the number of publications.
Not the number of publications. Yeah. It also happens. Not always, but I think now it's 4. So there are really few, very few remaining cases to complete the classification of non-single maximal curves of degree 8 up to isotopy, but in any case, it seems hopeless to expect such a classification in general. So in degree 8, this classification probably will be finished at some moment, but then there is degree 9, 10. In degree 9, some progress big progress was done, in particular by Korchagin, but then in degree 10, it's saying widely open as nothing. Okay, so let's now discuss deformation classification. So what do I mean by the deformation classification? So let's think in terms of the space of all curves of degree d in AP2. So let me denote it in this way. So this is the space of all, not necessarily non-singular, space of all curves of degree d in AP2. So you can easily identify this space with a real projective space of some dimension. And the dimension is d times d plus 3 over 2. Because each curve is given by a homogeneous polynomial, homogeneous real polynomial in 3 variables of degree d, and we consider this polynomial up to multiplication by non-zero real constant. So the coefficients of these polynomials can be taken as homogeneous coordinates of this real projective space, and to determine n, you should just count the number of possible monomials, subtract 1, and then you will get d times d plus 3 over 2. So in this space, there is, my picture is not realistic at all, but there is an extremely complicated hypersurface, D, which is called the discriminant. This is an algebraic hypersurface, and the points of this hypersurface correspond to singular curves. Once again, let's check that everybody is still with me. the points of the complement correspond to non-singular curves. Right? And so if we're interested in deformation classification of non-singular curves, in fact, we're interested in connected components of the complement of the discriminant. And by the way, now, with this schematic picture, we can come back to this discussion of the Harnack theorem. So now you can imagine how to prove, you can easily imagine how to prove the statement that if the upper bound is sharp and the lower bound is sharp, then all integer intermediate values can be realized as numbers of connected components of our curves. So you have some point in the complement of the discriminant realizing the upper bound. So the corresponding curve has d minus 1 times d minus 2 over 2 plus 1 connected components of the real point set. You have your, for example, Fermat curve given by this Fermat polynomial. And then to realize all the intermediate values, you can choose a generic path between these 2 points, and the generic path will intersect the discriminant transversally and only at points corresponding to curves, singular curves, but the most simple singular curves having just one singular point, and this singular point is non-degenerate double point, transversal intersector of two branches. And once you go across the discriminant at such point, clearly you change the number of connected components of the real point set by at most 1. Well, it's also clear that if I take 2 points in the same connected component of the complement of the discriminant, then the corresponding curves have the same topology of AP2RF, topology of this pair. Because if I have a path in the complement of the discriminant, I don't change the topology of my pair. But not vice versa. It's not true in general that 2 curves realizing the same topology of the pair are necessarily in the same connected component of the complement of the discriminant. So the first example you can find in degree 5, but I will present, since we are speaking about sextics, I will present an example in degree 6. The example is like this. So this is a schematic picture of one of my sextics. And this is a schematic picture of another one. So clearly the topology of the pair is the same. So we have one oval with 2 ovals inside and 2 ovals outside. But there is some extra information on my picture. So now I will draw something in green. So what I will draw is not a part of my curve, it's just some auxiliary line. And this auxiliary line I will draw, so I will pick one point, one green point, inside one of these exterior ovals, another point inside the other, and I will draw as straight as possible line through these 2 points. And the additional information on my picture is that this green line separates the interior of this big oval in 2 parts, and each of these parts contain an oval of my curve. And here, if I do such an operation, we are not in the same situation. So in particular, if you want, this line does not intersect the big oval. Is it clear for everybody that these 2 curves, so you should believe me that the both possibilities can be realized. If we assume it, does everybody agree that these 2 curves are not deformation equivalents? The corresponding points are not in the same connected component of the complement of the discriminant. Because if I imagine a path from one point to another. So if I can deform this curve to this one, this algebraic way, so, to find such a path, so my curve can have can take, so for this strip, my curve can take some additional luggage, this green line, and it's clear that at some moment of the trip, this green line will have to intersect the curve that I will have at this moment in at least 8 points, right? Because I have already 6 points of intersection, and this green line should somehow go through one of these ovals. And this, of course, is forbidden by the Biot theorem. There is another difference, in fact, between these two curves. So this curve is what is called type 1, and this curve is of type 2. About type 1, sometimes we'll say that this curve is separating. So what does it mean, type 1, type 2? So if you have a Riemann surface, so you think about the complex point set of our curve, equipped with anti-holomorphic involution. So this is the restriction of the complex conjugation to CF. So a fixed point set of this involution is the real point set of my curve. And it can happen that the real point set of my curve, the fixed point set of this involution, divides our Riemann surfaces in 2 halves exchanged by the involution, like in my picture. In this case, I say that it's type 1, but it can happen. Well, I'm trying to draw as pictures I can really draw. So this is not a picture of the complex point set of a non-singular sextic, right? Because the genus should be 10. Yeah. You should imagine more handles. And what can happen? So this is type 1, and what can happen? It can happen also that the complement of the real point set in the complex point set is connected. In this case, we say that the curve is of type 2. And so I claim that, in fact, this curve is necessarily of type 1, and such curve is necessarily of type 2. In fact, if you want to upgrade the isotopic classification of curves of degree 6, of non-singular curves of degree 6, to a classification up to deformation, the only information you need to add is the type. So if you know the topology of AP2RF, topology of the sphere, and the type 1 or 2, then you know the deformation type of your non-singular sextic. But starting from degree 7, such a statement is no longer true. So in higher degrees, you should add some other information. And by the way, so this deformation classification in, okay, let me write it once again. So deformation classifications in degree 6. So in the non-singular case, for non-singular curves, this classification was obtained by Vyacheslav Nikulin. In degree 5, such classification was obtained by Slava Kharlamov. In degree 6, by Nikulin, and the degree 6 is the maximal degree for which we know such classifications. What? That's, I agree. This is a philosophical question. So I repeat the philosophical question? Okay. I mean, there is a description or a list of the connected components of the complement of the discriminant. But I agree with you, it's always not clear what does it mean to know classification. So we know a list. But in fact, in the Nikulin's case, we know several versions of this list, and this list is somehow presented in an acceptable form. So it's possible how to, in particular, how to present this classification in a more or less short way. So there are 64 possible deformation types. So there are 64 connected components of the complement of the discriminant. But this 64 components can be presented in a more compact way than just a list of 64 components.
I think it is not precisely Nikulin what you say, because Nikulin make kind of arithmetical classification of case resources, of the corresponding case resources, and description of topology
Well,
for sextic. He did not know it, and he did not know how to do so. I think at least you should mention Nikulin and Kharlamov.
Well, so
In this case, it should be said Nikulin and Rokhlin. Because Rokhlin already knew the list, only the proof was missing.
Okay, I agree with you. We can. As I said, there are several ways to present such a classification. So this classification can be presented in arithmetical terms. I mean, the latest arithmetical terms. In this case, is definitely Nikulin. In geometric terms, of course, some reinterpretations of Nikulin classification was so the list was known to Rokhlin, and the interpretation was done by Slava. Kharlamov. So the arithmetical classification was done by Slava Nikulin, and the geometric interpretation by Slava Kharlamov. So now let's speak about singular curves. So you can discuss this deformation classification questions not only in the non-singular case, but also in singular. So you can consider singular curves, and you can consider equisingular deformations of these real singular curves. So the first case to consider is the case of curves with one non-degenerate double point. So the curves whose points lie on this main strata of the discriminant. And so curves with one non-degenerate double point. Right here. So this classification, I obtained this classification many years ago. This is an old story. I don't want to discuss this story today. So what I'd like to discuss in the remaining time is the classification we obtained with Alex Degtyaryov recently. And so this is a classification of sextics with smooth real path. So, in other words, now I'd like to discuss sextic curves that are probably singular, but I'd like these sextics to have smooth real path. I don't want to have real singular points. In fact, after this classification obtained more than 30 years ago of sextics with one degenerate double point, I didn't believe that it's possible increase the number of singularities for such a classification. But it turns out that if we assume that there are no real singularities, then it's possible to get a classification. So notice that if we speak about curves with one non-zero double point, since there is only one singularity, this singularity is necessarily real. Yeah? So, of course, the third case does not include the second one. Okay, so, of course, I will not present the classification, so hundreds of types, but I would like just to explain how this classification can be obtained and how this classification can be organized. And so now let's speak about real singular sextics. So we have a real singular sextic, but even if we start with, let's start with a complex singular sextic. So we have, let me denote it by, I don't know, C. So it's a singular sextic. And let me assume that the singularities are simple. So only of A, D, E type. For this classification, you don't need to add this restriction. You can just treat separately non-simple singularities, since I require my curves to have singularities and not to have real singularities. So if I have a singular point, I have necessarily another one which is the complex conjugate. And so if I assume that my singularity is non-simple, so I have another one, singularity of the same type, it's easy to see that the only possibility is to have a singularities of type times called J10, so quadratic tangency of two branches. And in this case, your sextic is necessarily a union of three conics, so it's easy to obtain the deformation classification. So let's assume that singularities are simple. So in this case, so first of all, you can consider the ramified double covering of CP2 so branched along the complex point set of our sextic. And then X is a minimal resolution of singularities. So X is a K3 surface. Yeah, so we can use the standard machinery of K3 surfaces. So we can use this package, including the global Tarelli theorem, the surjectivity of the period map, and some results of Saint-Donat to reduce our problem about the deformation classification to some latest arithmetic problem. And so what? I'm sorry? Global Tarelli theorem, the injectivity of the period map. For K3 surfaces. No, so now we work with this K3 surface. So the second homology group of this surface with integer coefficient considered as lattice is isomorphic to 2e8 plus 3u. So e8 for me is a negative definite lattice, and u is hyperbolic plane. So, okay. So in an appropriate basis, the Gram matrix is 0, 1, 1, 0. So now in this lattice, you have some elements. So you have S, the sublattice, so it's root lattice generated by the exceptional devices. Then you have the polarization, so the pullback of the class with the line. What? Self-intersecting roots are of square minus 2. So this lattice is even. So the polarization, so our K3 surface is too polarized. And so S is orthogonal to H. If you consider the direct sum, you have a sublattice in H2 of X. And I'd like to consider the primitive hull of this sublattice. So the primitive hull of let's denote it by SH. Okay, so now we have, so for the moment everything was complex, but we are interested in real curves. So in fact we have, now let's assume that our curve is real. We have the involution of complex conjugation on CP2. And if our curve is real, this involution of complex conjugation lifts to X, even in two different ways. Let's assume, moreover, that my real curve is with smooth real path, so now we're in this case. And as I hope you remember, so I defined AP2 plus and AP2 minus only in a singular case, but in this singular case, they are defined in a completely similar way. And once again, since my curve has smooth real path, I can again distinguish between AP2 plus and AP2 minus. So one of them is orientable, so it's still my convention that it's AP2 plus. And the other one is AP2 minus. It's not the crucial place where I use the assumption that the real path is smooth, but since the real path is smooth, in particular, I can distinguish between AP2 plus and AP2 minus, and these two liftings, so these two liftings of the complex conjugation of CP2 to X, so for one of them, the real path leaves over AP2 plus, so it's projected to AP2 plus, and for the other one, the real path is projected to AP2 minus. So let's consider the lifting such that the real path, the fixed point set, is projected to AP2 plus. So is the lifting of the complex conjugation of CP2 the lifting such that the fixed point set is projected to AP2 plus. And so now we have the following quadruple. So we have H2 of x. In H2 of x, we have this primitive hull. In the primitive hull, we have H, and I also have, so this is the involution on H2 of x induced by this lifting. So we have such a quadruple. And this quadruple is called real homological type of the sextic under consideration. So once again, I assume that my sextic is real with smooth real path. And the theorem we proved, in fact, the main ingredient in the classification we obtained with Sasha Degtyaryov is the following statement. So the real homological type of a real sextic with smooth real path so this assumption is really crucial. With smooth real path determines the deformation class of the sextic. So, in fact, two real sextics with smooth real path are equisingular deformation equivalent if and only if they have isomorphic real homological types. What time should I finish? Right now? Okay, couple of minutes? It's still around now? Okay, so this is the arithmetic, latest arithmetic part of the classification. And the proof is, well, as I said, you use the standard, this standard package, global Taylor theorem and surjectivity of the period map for K3 surfaces. In fact, what happens in the proof of this statement is that if you work with the period space of the corresponding K3 surfaces, so you want to understand this deformation classification, so you know, so you have some walls in the period space, and if you're interested in deformations of your objects, you should try to go across these walls. So, for example, in Nicoullis classification, you can easily go across any wall you need to go just using a reflection. So it turns out that under this assumption, you can once again, in your period space, go across the walls. The automorphisms are much more complicated than just reflections, but still you can prove that you can go across the walls, and then this lattice arithmetic classification can be interpreted in geometric terms, at least partially. So it's possible to try to understand some topological invariance distinguishing different deformation classes. So you can play with types, one or two types of components, distribution of intersection, well, singularities between different halves. It's not enough, but still it explains at least partially this classification. One can make some extra observations looking at this classification. For example, it was already known since this second classification of sextics with one degenerate double point, that any empty oval of a non-singular sextic, empty meaning that it's an oval without any ovals inside, any oval of a non-singular sextic can be contracted to a point. So you can go to the corresponding wall of the discriminant. And so the similar statement is true for sextics with smooth real path. There are also some congruences similar to Gutkov-Rokhlin congruence I discussed, which are valid for these curves with smooth real path. You should just add one assumption that the singularities you want to consider are locally reducible. For locally reducible singularities, you have some congruences of this Arnold Gutkov-Rokhlin type. And the last thing I would like to say is that this assumption that the real path is smooth is really crucial. So even if you think about sextics with one non-degenerate double point, you can of course consider real homological types, but such a statement is completely wrong already with one non-degenerate double point. So it's really particular statement in this case of sextics with smooth real path. Okay.
Questions to Ilya?
So you said that you had to have this generalization of Rokhlin congruence.
Mm-hmm.
You had to have some about the singularities.
Yeah.
About it is only technical or it is necessary?
No. It's so if you, well, I don't know to what extent this congruences are true. So what are possible generalizations? But some restrictions you should add. So if you just allow any singularities, still speaking about smooth real path, in this case you don't have these congruences. You do have them if the singularities are of. Okay, so it's just a short way to say that we want locally reducible singularities, but since we are speaking about simple singularities, ADE type, so it means that we want to have A to N and E6 and E8, right?
Thank you.
More questions to Ilya?
What about maximal curves?
Maximal curves? You mean maximal?
The maximal curves.
Well, there are many of them. How many? Well, I can try to look at the list and to check what happens. But well, I think that it's definitely more than 10, but not much more. And for
most interesting.
Of course, of course.
So it stays that we investigate this. But other, okay, can you give some interesting components in this model space? What are the interesting components? There are many components, but some of them are more interesting than the others. Which one are interesting?
Well, so in fact, the answer to your question depends on what do you mean by interesting. So,
What you mean?
no, the question is yours. And the answers indeed are mine. So they depend on your meaning of interesting. Because I agree with you. In a sense, the most traditionally, the most interesting cases are maximal and close to maximal. And indeed, it's as it happens also in the case of non-singular curves, maximal should be understood in a wider sense. Right? So you always describe such a classification going from some upper cases, you're going down. And so there are some cases which are maximal, so the upper cases which are maximal in the sense I described. And there are some other maximal cases, meaning the highest cases. They're indeed interesting, but it seems to me that the most interesting cases in this classification are on the opposite side. So it turns out that if you are close to the maximal case, you can easily describe this classification in topological terms. If you want to have some complicated pairs of deformation classes that are difficult to distinguish, at least there are some pairs for which I don't know how to distinguish them topologically. They are rather close to empty curves. I think that the empty curves, in a sense, are the most complicated, the most interesting case in this classification. Empty meaning that there are no real points at all. Particulars.
Just to finish with my question. Okay, so how to understand interesting? There are different ways. For example, I may ask about the topology of a given component in the model space. For example, are there components which are simply connected?
Yeah, I agree. This is a very good question. So our next goal, indeed, is, and we didn't do it for the moment, is to try to understand the monodromy of these components. So this is definitely doable, but we didn't do it. And I agree with you. It's natural to expect that the most interesting answers will be close to the maximal case, of course.
Okay, if you have more questions, we can ask during the coffee break. So let's thank Celia again.